In this video, let's tie these different reactions together. We learned a lot of individual bits and saw a little bit of how different molecules can change their functional groups, but let's talk about how we can use that. What we've learned is a series of individual steps, individual changes of a functional group. When you have a very simple molecule, it's a little easier to see. I have propene and I add water. That is, what will happen to it? Well, we have to think, hey, what is my functional group? So your very first thought is to find your functional group. Well, I have an alkene. What do we know alkenes can do? We had a small series of reactions for them. I had that an alkene plus H2 can become an alkane. I had alkene plus H2O could become an alcohol. I had alkenes plus dihalides could become haloalkanes. And I had that a double bond plus a haloacid could become haloalkanes as well. So these were the reactions we had for double bonds. Which of these might apply here? Well, only one of them uses water. So most likely, if I have a double bond plus water, I am forming an alcohol. This is what the tools we've learned let us see. We really just have a series of reactions for converting a functional group to another one. So by knowing what functional group I have, I can then determine what reactions are possible. RxN for reaction. So I'm going to end up with an alcohol for my molecule. I have converted one functional group to another. Now, if I had a larger molecule, let's look at this. This molecule has two functional groups. It's got a carboxylic acid and it's got a double bond. If I say I add water to it and let it react, and we're told it does react, well, what could it do? First thing is to look at my functional groups. Well, my functional groups are, hey, there's a carboxylic acid, and there's an alkene. Do either of those react with water? Well, we just said yes with the alkene. If we think about our carboxylic acid reactions, none of them reacted with water. So you could react it with alcohols to make esters. You could react a carboxylic acid with an amine to make an amide. You could break an ester with water to get a carboxylic acid, but carboxylic acids didn't do anything with water. So nothing will happen to the carboxylic acid, but that double bond does react with water. And so my carboxylic acid part will remain unchanged. All of my alkane carbon-carbon and carbon-hydrogen bonds will remain unchanged, but that double bond, now it could do something. And so I'll either get this, or since there's more than one spot that OH could add to, it could have also gone down. And there are more hydrogens not shown. We're just showing the ones that came from water. What we've done is we looked at a molecule and we said, all right, what are the functional groups present? We've identified them. Then we looked at the reactant. What is the other chemical that could do something with these? We compared them. We said, well, nothing will happen with carboxylic acid, but something can happen with the double bond. And we drew the possibilities of what occurs to that double bond. This is how we leverage those individual tools to see what happens on larger, more complex molecules. I don't need to know what water does with this particular molecule, and I don't need to know that for every single unique pairing of every molecule in the universe. I just need to look at what functional groups are on the molecule. So if we had an even more elaborate, much larger molecule, I don't need to care about the fact that this is one we've never seen before. Again, I look and I say there is a double bond and there is a carboxylic acid. So if this time we are adding NH2 ethanamine, well, I look at these and I say, hey, again, there is a carboxylic acid and there's an alkene. All of the alkanes in the middle, they don't do anything. Do either of these care about a primary amine? We don't know anything in our alkene tools that care about primary amines, and so we're going to assume that nothing's happening there. But a carboxylic acid plus an amine, or generic carboxylic acid plus the generic amine, will form an amide. And water. So there's a reaction here that can occur between our carboxylic acid and the amine. And so what will this molecule look like after it reacts? Well, all the parts that didn't react will be left alone. And the parts that did react will look like whatever their new form is. So regardless of how many functional groups, how strange the shape of the molecule, what we're really always doing is we are looking at the functional group of the things that are there and saying, what could they do if they were brought together? What could an alkene and an amine do? Nothing for what we've been taught. A carboxylic acid and an amine, what could they do? Oh, they could form an amide. How would it look if they reacted? Well, the OH would have to be displaced. The amine would take its spot to form the amide. For all of the tools that we've learned in the previous videos, this is the approach for whatever molecule you're given to solve what will happen when it reacts. First, find that functional group, and then check what reactions are possible with that functional group and the second molecule. And so for our alkenes, here's a little short list. We can build this kind of short list for all of our functional groups. You've got your alkenes. For our alcohols, there were a few options. We could dehydrate with some heat and form a double bond. For our alcohols, we could add some heat, a little bit more catalytic acid, and form our ethers. For our alcohols, we could add an oxidant and get an aldehyde. For our alcohol, we could add 2 equivalents of oxidant and be certain of getting a carboxylic acid. And for an alcohol that was a secondary alcohol, we could add an oxidant and get a ketone. And so here's a series of tools for when we see an alcohol group. If our molecule looks like this, I've got a double bond, I've got an alcohol, and heck, let's add carboxylic acid onto it. And one more. Let's add a halide. Here is a bunch of different functional groups on this molecule. If I add oxidant, what will it become? Well, we look and we identify each of our functional groups. Alkene, haloalkane, carboxylic acid, alcohol. Well, the only things of these functional groups that react with oxidant is the alcohol. We didn't have any rules for double bonds and oxidants. We didn't have any for alkyl halides and oxidants. And carboxylic acids are the end product of oxidation. They're already done. That alcohol is the only one that will react with this. Well, the rest of the molecule then isn't affected. They didn't do anything. So we can put them all in as they were. And now it's that what was the OH? Well, it was a secondary OH, so it's going to become a ketone. And so how does this rather complex molecule react to an oxidant? We don't have to care. We just have to look at the individual functional groups and say, what would each of them do to an oxidant? Now this can have slightly complicating multiple reactions. have a double bond, halide again. But what if this time it was an aldehyde on bottom and an OH? And I go and add oxidant. Generally, when we add oxidant, we assume we add excess. And so often you'll see it written as excess oxidant. You can try to be very precise, but except for very few oxidizing reagents, that's a little bit difficult. And so, given that we're only talking about oxidants in general, we're going to assume we always have sufficient excess oxidant. So anything that can react with oxidant will. Well, again, I have an alkyl halide. They don't react with oxidant. I have a double bond. They don't do anything. But an aldehyde will, and my alcohol will. Both of those will react with oxidant. So as I draw my new molecule, well, all the carbons that weren't part of the reaction will stay the same. All the chlorines that weren't part will stay the same, the double bond. But now I have my aldehyde. It becomes a carboxylic acid, and my alcohol, much like last time, becomes a ketone. And so in this case, we actually made the exact same product from two slightly different starting materials. One just had already had the aldehyde turned to a carboxylic acid, and our lower one, it was still an aldehyde that could react with oxidant. It's possible that more than one of your functional groups will be capable of reacting with the reactant. If that's the case, just identify what it will do and translate that into the product. As we continue down our list then, so we have alcohols, we've had our double bonds, aldehydes and ketones really just oxidize or don't. Our carboxylic acids really only had a few reactions. You could add alcohol to form an ester, or you could have a carboxylic acid, add amine. Primary, secondary work just fine. I draw primary a lot. There's no reason you can't do this with a secondary. If you do, you will get an amide. Generally, primary amides are just easier, which is why I've been drawing so many of them, but you can form secondary amides as well. You can't form tertiary amides. See if you can think about why when you do it. Hint, how many bonds is nitrogen forced to have? But in our cases, we have a few tools for carboxylic acids. As a result, if you had a molecule, and to this molecule you added ethanol. Again, we have to look and say, well, what can this molecule do? What are the functional groups? I've got a carboxylic acid. I have a second carboxylic acid. I have a double bond. There are three main functional groups on this molecule. The rest is alkanes. Do any of these react with alcohol? Well, double bonds, we didn't learn anything that they do with alcohol. But carboxylic acids will. They'll form esters. Oh wait, I have two of them. Well, I have plenty of ethanol, so they both react. And two waters. What happens here is that our dicarboxylic acid becomes a diester. We have two esters on the same molecule. The double bond was unaffected, and so it remained unchanged. Again, all we needed to look at was our functional groups. We didn't have to be concerned about the whole molecule and how it reacts with alcohol, because we don't know. We've never learned whatever this molecule's particular reactions are. But we can determine what it will do with alcohol by looking at its functional groups. So all of the individual reactions are really separate tools for identifying what that functional group will do with another reagent.